Hey everyone, my name is Michael, and the paper I chose to dive into was Pruning versus Quantization and trying to discover which is better. This was a research paper by Qualcomm's AI team, and it was published in the 2023 proceedings, so quite recent for the neural PS. It aims to quantitatively compare pruning and quantization. This isn't something that's really been done before, at least in terms of a one-to-one comparison, so that's kind of what their goal was with this paper. And it is quite novel in the sense that it provided some pretty valuable insight, which we'll get into in a minute. I would like to point out that I will make this slideshow as well as the paper available in the post if you want to go and check out any of the links that I have. So as I mentioned, there hasn't really been any direct or tangible comparison between these two compression methods. So given that in the real world there's quite limited time to do things like network compression and optimization, it's worth trying to discover which one of these methods is superior and why. And so having a way of informing decisions made on neural networks moving forward for things like hardware efficiency and performance optimization is key. A couple more reasons that I listed down and could think of and that were listed in the paper are bulleted and bolded, but I would like to point out that the cost efficiency and developer support is definitely good. One thing for the developer support I'd like to point out that we'll get into as well is that one of these methods lends themselves very well to very quick and easy improvement, while the other requires some sort of overhead. And we'll talk about that here right now. So quantization, we're going to get into some quick definitions before we go into the actual paper, because I think it'd be useful to have some context before jumping into the improvements. So quantization reduces the precision of weights in a neural network. And what this really just means is that you're reducing the bit width, or the number of bits required to represent a number. This is incredibly useful because it means that you can store more numbers within the same amount of memory. And this significantly reduces model time or size and compute time. And it can enable things like SIMD as well as some other compute efficient operations. So the figure on the right is just kind of depicting this here, where we have floating point numbers that are being rounded off to the nearest integer from what it appears. And typically the way that this is done is sort of on a linear scale centered at 0. But there's quite a few different quantizations methods, but the most common one is sort of the intuitive approach that you would think, where you're just sort of rounding numbers to the closest number that the bit will allow, or the width of your bits will allow. And pruning is somewhat similar to quantization in the sense that instead of reducing all of your weights of bits, you can just set some of them to 0 instead. And you retain the full bit width for all your numbers. But what this does is, in things like weight matrices, it results in sparse matrix, and those are usually very quick for computations. And the way that we do this typically requires further training, whereas quantization, you can just immediately reduce the bit width. And both of these, you will typically find that you lose some accuracy unless you're already overfit on your data. But we're trying to discover which one really does better in terms of accuracy loss. And so the way that the Qualcomm team decided to go about this was by taking floating point 16-bit models and weights and compressing them, either using quantization, where you're reducing your bit width, which is this left column on the table, or you're pruning the network, meaning you're cutting out a certain number of the original weights, and that's this middle column. And what they're doing is they're effectively saying that a 2x compression is equivalent if you're reducing the bit width by 2, or I guess by 1/2, or you're removing half of the weights in your neural network. And this makes sense intuitively, at least, right? So it makes sense that this is a fair comparison to make. And you can see that these were all the values that they tested from 2 to 8 in terms of bit width, and the respective amount that needed to get pruned for that compression ratio. One thing I would like to point out is that the performance metric we're using is signal noise ratio, and this is calculated here using this big equation for 10 log base 10, followed by the numerator is going to be your signal. What this means in the context of our problem is it is going to be the original error caused by the network without any sort of compression, and the denominator, or the noise, is going to be the error with this compression, whether it's quantization or pruning, which I've included both of those equations down below. So the expected MSE or mean squared error for quantization is defined by this large sum of integrals. The left term here corresponds to the rounding error, while the right two terms correspond to the clipping error. This is pretty standard. One thing I would like to point out is that because this is an analytical or theoretical approach, you can get pretty close and accurate results without actually having to run any experiments. And we'll see that the experiments are reflected in, the experiments reflect what we would expect, and we'll talk about that in a little bit here. We also have the expected MSE for pruning, where we're going to have some threshold value for how much is getting cut off, which is t in this case. So the theoretical error analysis is visualized very nicely here in these three figures. So moving from left to right, one thing I would like to point out is that when you initialize a weight matrix for training, it's typically Gaussian shaped, as any random thing is. So the weights here, you can see that the original is centered at 0. It's just a normal distribution. And by quantizing it, we're effectively snapping these values to the closest integer, 0, 1, 2, 3, or not integer, but nearest precision, right? So in this case, what they're plotting was int4 quantization versus 75% pruning, and those are both the equivalent 4x compression ratio. So we can see that the quantized model does a really nice job fitting the original shape, which we would expect. And then the pruned model, as you would also expect, cuts off everything that isn't the tails. And the reason that it's doing that is because it's only taking the most important, I guess you could say, weights and keeping them and setting everything else to 0. And again, the squared error that's associated with that change is reflected in the middle graph. And these are the pruning results. And you can see that as we're getting farther away from 0, the error is going to be much higher. And that should make sense, because until we stop pruning, the farther away you get from 0 and you're setting those values to 0, these weights, I should say, you're effectively losing more and more information. If I'm pruning a weight that has a value of 0.001 versus a weight with a value of 0.5, the one that is 0.5 is you're losing a lot more information in that because it's a much larger change. With that being said, the result when actually doing the theoretical analysis for that signal noise ratio that we explained calculating earlier, that's on the far right. And as you can see here, quantization has a much higher signal noise ratio, and that's a good thing. In this case, signal noise ratio, again, as we said, is going to be the uncompressed error over the compressed error. So having a smaller compressed error means that it's doing our compression method is doing a better job. And we can see that here, that quantization is outperforming pruning pretty well. And I'll just say now that this is a theme that we're going to see throughout the rest of this presentation and the paper. One thing I want to get into before we talk a little bit more about the theoretical and then actual error is kurtosis. So kurtosis is a measure of tailedness. You can think of it for normal distributions or Gaussian distributions. And what this means in the context of our networks and our compression is it's a measure of outliers. So if you recall from the Gaussian distribution, having more values in the tails here, especially if we're looking at this left figure, means that the pruning isn't going to affect it as much, right? Whereas quantization, it might get a little bit more affected by, and the reason is because pruning is not touching those values. It's perfectly matching the original distribution as we're getting farther and farther away from the mean. So in the context of evaluating models, the kurtosis of a weight tensor is really telling us, that these weights would be strongly affected by pruning if there's a lot of outliers. And for those who are curious, the numerator is the fourth central moment, and then that's to the fourth power, divided by the standard deviation. So with that being said, as I kind of mentioned, having pruning for high kurtosis values is actually pretty effective. And the reason for this is because it's not affected as much by having these outliers. Pruning is not going and cutting those weights. So this left figure here is showing us that pruning signal noise ratio is not really affected by high kurtosis. We see that as we're moving along the x-axis on this left figure, for any given compression ratio, which is our y-axis, there's not much change in color. And change in color here means the signal-noise ratio. Whereas if you look at something like quantization, we see a large change in color, or a large change in signal-noise ratio, implying that as we have more tailedness in our distribution of weights, we're going to run into a much larger change in our signal-noise ratio, and a negative change at that, something that we're not looking for. In this case, we're going to the darker, cooler colors, which are, in the context of this graph, bad. So what this is telling us, and what the team at Qualcomm did with this really nice graph here, is they plotted out and basically said that for higher compression ranges, and when there's many outliers in our distributions, pruning may perform better. And when we're looking at the experimental results, which we'll see in a second here, we find that that's actually the case. But you can see that for the most part, for a large majority of this graph, quantization is going to perform better. And that's what we see here. So what the team did is they ran this experiment on 46 of the Model Zoo PyTorch Model Zoo weights, or 46 PyTorch models, as well as 3 large language models. And so what this graph on the left is showing us is that as we move along the x-axis, this is our quantization signal-noise ratio, and the y is our pruning. And this sort of diagonal line here is insinuating that anything above this line, pruning is going to perform better, and anything below the line, quantization is going to perform better. And this is because this is the ratio between quantization and pruning SNR. And as you can see, as we're increasing our compression ratio, going from cooler to warmer colors on the graph, so you'll see that it actually does start to approach more of a common ground, which is what you'd expect, and that's what's evidenced by the right graph, right? As we increase our compression range for the equivalent number of bits, being 2, or a high pruning value of that would be an 8x compression. Pruning is going to perform better as we have more tailedness in our distributions. With that being said, you can see that for the most part, quantization is definitely doing better, and I would like to point out how closely related the experimental and theoretical graphs are for these right figures. So if I'll just go back really quick so you can see that the team did a fantastic job sort of using math first and analysis to predict sort of the expected behavior, which is what we're seeing here. The team also did layer-wise theoretical analysis, which I thought was really interesting. Basically, this was, instead of looking at only the weights, they were looking at the activation layer for SNR. And we can see again that quantization outperforms pruning at lower compression ratios, and then as it sort of gets higher, as the compression ratio increases, pruning starts to perform a little bit more comparably, but quantization for the most part is still outperforming it. In the paper, sections 4.1 and 4.2 describe how these bounds were defined mathematically. It's super clever, but beyond the scope of this presentation for the sake of time. So with that being said, after that, what the team did is they went and looked at a handful of real-world models, and they just went and did these compression ratios and evaluated their accuracy. And what they found was, again, for the most part, that quantization is more beneficial due to a larger gap in performance, as per what they said in their paper, and we can see that with the bolded values, that quantization for the most part was outperforming everything. I think the only exception here was ResNet 50, and even so, quantization performs comparably on these metrics. So it's safe to say that for the most part, quantization was the superior method, and that's kind of the bottom line here, is that unstructured pruning rarely outperformed quantization. It was only under very niche compression ratios and niche cases of high kurtosis weight distributions. And it also requires memory overhead that was not really talked about in the paper. So the discussion in the paper is phenomenal, and I would encourage you to read it. It kind of adds some very nice points and bottom lines, but one thing that I also thought was interesting that they touched on is that the hardware optimization considerations were ignored, and they'd provide a more holistic understanding of kind of how this how these two compression methods work and how they would compare. With that being said, my 2 cents on that matter is that quantization is very straightforward, whereas something like pruning, as they mentioned, requires memory overhead and additional processes. Now, there is two different methods of quantization. There is quantize-aware training, and then just straight quantization, where you just cut the model weights and ship it as is. But typically what you'll want to do is quantize the model and then train it. So the fine-tuning with pruning versus quantize-aware training, we'll say that they're comparable for that. I would be really curious to see if they took that any further, and I would like to see sort of next steps in that field. But for the most part, I would say that for now, we have a very clear winner in terms of the better compression method, and that's kind of their sentiment that they shared. One thing that I wanted to share is that I like quantization a lot because it makes hardware acceleration like SIMD more possible, whereas pruning, you can utilize sparse matrices in unique ways, but it may not be as straightforward for the hardware engineers. I would also really like to see, them try and test the quantization on different things like FPGAs or system on chips, and kind of see how that changes things, if at all. I do have quite a handful of questions, and some questions that I would encourage you guys to try and answer. My number one question, if anyone's been paying attention to optimization research lately, is that 1-bit or ternary bit quantization has been shown to be pretty effective in some large language models. And this is an extremely high compression ratio from something like floating point 16. Bordering on the magnitude of 16x, which is quite impressive that you could make a model that much smaller and still have comparable results. And it begs the question, given that we were talking about pruning performing well for extremely high compression values, would the results change? My guess is that they wouldn't, but that's something that would require further exploration for sure. I have a handful of other questions. I encourage you to read them and sort of take a crack at them, and also just sort of share your thoughts. I'd love to hear what you think about this sort of work, and if that's something that you're more interested in. Here's the citation for the one paper. It's the paper that will be linked. As I said, this presentation will be available as well if you want to go and look at any of the links that I included. Thank you very much for watching. I hope you have a nice day.